Okay, let's get started on a new chapter, and we're going to talk about linear transformations. Now, I can preface this by saying that linear transformation is to vector space the same thing as a function is to a set, say the set of real numbers or the set of integers. Linear transformations take you from one vector space to another. We know that if we have a function, you have f, you have the domain, and you have the codomain, or the range is a subset of the codomain. Linear transformations are similar. Linear transformations take you from one vector space to another vector space. Now, naturally, this is a very important concept. You know that in calculus, you talk about functions. That's all about functions. So, a very important aspect of linear algebra is linear transformations that take you from one vector space to another vector space. Okay, so as he says that these linear transformations are just as fundamental as the vector spaces themselves. All right, so let's go on, and of course we're going to define linear transformations. And here we have it. Definition of linear transformation. Okay. So a linear transformation is a function that carries elements of the vector space U to the vector space V. Okay. So we have our usual notions of domain, which is U, codomain, which is V, that has two additional properties. So it's a restricted type of function, special type of function. And here the properties are. The linear transformation applied to the sum of two vectors is the sum of the two individual linear transformations. This certainly looks familiar. We have this kind of vector space property stuff. It's like that. It's kind of like the linear transformation distributes over addition, you could say, sort of. Same thing here. You have the linear transformation applied to the scalar multiple times the vector is a scalar multiple times the linear transformation. Okay, so we can describe this as saying a linear transformation preserves addition and scalar multiplication. So what do we mean by preserves? It basically means we can add before we take the linear transformation, or we can add after we take the linear transformation. We basically get the same result. Same thing with scalar multiple. We can scalar multiply the vector before we take the linear transformation, or we can scalar multiply after, and we get the same result. Okay. Let's look at an example. Well, I take that back. Let me follow the flow of the book. There are several examples later on. Okay. So here's some diagrams that are very useful, and you see these types of diagrams a great deal in higher mathematics. All right, now in this diagram, here we start out with u1 and u2, and we have the function plus that takes us to u1 plus u2. Now notice that all these vectors are in big U, so I can kind of divide this diagram into two parts. This part is in the U world, and the other part is in the big V world. You could think of U world as United States and V as Venezuela. All right, in the U world, people speak English. And we have this English plus, where you have two things get together and you add in this in United States world. But you can do a translation. You translate into Spanish. Okay, then if you translate these two words into Spanish, you get Spanish word 1, Spanish word 2, and you can add these two together, and then you get a result. So you can think about this in in terms of a language, for instance, suppose U1 and U2 are words. U1 is dogs and U2 is bark. So you have dogs, bark. And then you add them together and you get the sentence dogs bark. Now you could translate dogs to Spanish, whatever that is. You can translate bark to Spanish, whatever that is, and you put those together, and presumably you still get a sentence that means dogs bark. Okay, so this kind of function is sort of like a translation. And it basically says that for linear transformation, you can work either in the U world or in the V world, and you end up with the same result. All right, so the same thing here. This is for addition. This is the diagram for addition. And here's the similar diagram for scalar multiplication. This is the U world. And this is the V world. Okay. So you take U and multiply by alpha. This, you're doing all of this in the U world. Presumably you can take U and translate, and then multiply in the translated world, and you'll get the same result whether you go this way or this way. You get the very same result. Okay, very common. This sort of thing is called a commutative diagram, and you see this a great deal in higher algebra. Okay. All right, so here some details. T is the name of the function. If we're applying the function to a particular vector, we call it T of U. Okay. I think it's clear what's going on here, that when you talk about T of x plus y, you're adding the vectors first and then taking the function. Here you're taking the function of the first vector and then adding that to the function of the second vector. All right, so let's go ahead with some examples. All right, here's a linear transformation. When you talk about functions, you do talk about outputs and inputs. So in this case, the input is a three-dimensional vector, and the output is a two-dimensional vector. And here's the rule that gives you the output from the input. If I input x1, x2, x3, I output this two-dimensional vector, taking the combination 2x1 plus x3, putting that in the first component, minus 4x2 goes in the second component. All right, so let's check these properties. It's really just plug in and see if it works. Here we have a rule, and we apply this rule and see if this rule satisfies the linearity properties. So to do T of x plus y, first we have to add x plus y here, use our usual rule for vector addition, then we apply T to it. Now what is the rule for T? T says take 2 times the first component plus the third component. Now in this case, the first component is x1 plus y1. So I have to take 2 times x1 plus y1. And then I have to add the third component. Third component is x3 plus y3. So here I get plus x3 plus y3. Okay. Same for the second component. Second component here, the rule is take minus 4 times the second component here. Well, in this case, when I'm applying T to this vector with x1 plus y1, x2 plus y2, x3 plus y3, the second component is here. So to apply the rule, I have to take minus 4 times the second component, which is exactly what happens here. All right. So let me clear away some of this junk so you can see what's going on. Okay. All right, so this gives us our result, T applied to the sum of the two vectors. Let's rearrange. Let's group the x terms and the y terms. All right, this is just simple rearrangement, and then we can break this apart into two vectors as we've seen before. We take the part with all x's and the part with all y's, and then notice that actually this vector, I could obtain this same vector by applying the rule T to the vector x1, x2, x3. And I could attain this vector here by applying the same rule here to the sole vector y1, y2, y3. So that gives me the result that this is equal to T of x plus T of y. Okay, linearity. Okay. All right, so that's the linearity of addition. If we do linearity of scalar multiplication, let's apply the same rule. To T of ax means we take T of this scalar multiple times the vector. Scalar multiple times the vector means I can multiply each component by that scalar multiple. Then I apply the rule. This is applying the linear transformation rule to the vector alpha x1, alpha x2, alpha x3. Right? Then I know I can factor out constants, so I factor out this constant. I can take the constant outside, and it turns out that this is alpha times the rule t applied to the vector x1, x2, x3. So you'll be verifying this kind of verification for several linear transformations. Right, here's a case where we have another example. It turns out not to be a linear transformation. Okay, so this is my function. This is my rule. It takes a three-dimensional vector to a three-dimensional vector this time. Okay, this has x's. Depends on x's. Looks a little different. Here we have a 0, and here we have a -2 that has no x coefficient. Notice that if you want to relate this linear to the notion of linear that we have before, for instance, we had y equals mx plus b. And this is the equation of a line. This is called a linear term because it depends on x to the first power. You have linear terms, quadratic terms, and so on. This is called a constant term. All right. And strictly speaking, in this context, we don't call that a linear term. It's a constant term. So you can see that, and we will see that linear transformations are functions that have all linear terms. They always have the variable to the first power. Okay, and we can see that we don't have that situation here, and we'll see how that makes us into trouble. So for instance, let's take an example of 3 times the rule s applied to the vector 1, 2, 3. All right, applying the vector s, the rule s to 1, 2, 3, I have to take the first component is going to be 4 times 1 plus 2 times 3. Okay, I'm sorry, not 2 times 3, it's 2 times 2 because x2 is 2. 4 times 1 plus 2 times 2. 4 times 1 plus 2 times 2 is 8, so we're good with that. Okay, for the second one, the second component is always 0. Third component is going to be, let's clear out the junk so we can see what's going on. Okay, third component is going to be x1, which is 1, plus 3 times x3, which is 9. So that's giving me, let's see, am I right here? I have 1 plus 3 times x3, which is 9, minus 2. Okay, that's going to give me, what did I say? 1 plus 3 times x3. So 1 plus 9 is 10 minus 2 gives me 8. So we're good with this. If I multiply that result by 3, I'm going to get this 24, 0, 24. Now, on the other hand, if S is a linear transformation, I can multiply first and then apply the rule. If you do that, you'll end up with something that's different. These two are not the same, so that means it's not linear. Okay. All right. And here he notices that it's this constant term minus 2 that screws things up. It's actually not the 0 that screws things up. 0 I can consider as 0x5. Okay, I'm sorry, 0x2 or something like that. 0 is still a linear term. The problem is this constant term that's not a linear term. Okay. Here's another example of linear transformation. Starting out with polynomials. Okay, start out with a polynomial. And then I can define it as a function. I can take a function from any one space to any other space I want. So I'm going to take polynomials to 2 by 2 matrices. All right, so here's the rule. I define the 4 entries of the matrix in terms of the coefficients of the polynomial in this way. You can go through and verify these two conditions. Okay, so I invite you to read this. I'm going to be lazy and not do it myself, but it's the same type of verification. You apply the rule to the sum of 2 polynomials. So take the sum of the 2 polynomials first, then apply the rule, and show that's the same thing as taking the rule applied to each individual polynomial and summing the result. And same with scalar multiplication. Okay, here's another linear transformation. You can read through this. Not similar example. Okay. All right, so let's start proving properties. And these properties make it simpler, and it shows us what's really going on when we do these linear transformations. Okay, so here's the first property, that linear transformation takes 0 to 0. If I have the 0 vector in my domain vector space, and we know every vector space has a 0 vector, so there's no problem with that. So if I take linear transformation applied to the 0 vector in the domain, that's going to give me the 0 vector in the range. So this 0 here is in U, and the other 0 here is in V. Right. So what's the proof? Well, let's apply one of the linear transformation rules. We know that this rule that T of alpha V is equal to alpha of TV. And this has to be true for any alpha and any V. All right, so we're actually going to apply it to the 0 vector in U. All right, T of the 0 vector in U. Now we know already that the 0 vector in U is the same thing as 0 times the 0 vector. But here we have T of alpha V. So I can bring the alpha out, it gives me 0. And 0 times any vector is 0. So T of 0 U must be 0 V. And we finished our proof. Okay. So this shows us why this function S doesn't work. If you remember this constant term that we had in the function back here, this constant term minus 2 means that no matter what you put in, you're going to have a minus 2 here. If I put all zeros in, I'm going to get a minus 2 out here. That's no good. If I put a 0 in, I have to get a 0 out. So that shows why that one fails to be a linear transformation. All right, I'm going to go ahead and do this subsection because it's kind of small. This basically says, you've seen these sort of function diagrams. And what he's saying here is that this is a good way to represent what happens in a linear transformation. You always have the 0 vector in your domain going to the 0 vector in your range. That's always true. And you always have elements of the domain going to elements in the codomain. And it's possible that 2 elements in the domain may go to the same element in the codomain. It's not possible for 1 element in the domain to go to 2 elements in the codomain. That's not possible because functions don't act like that. So this is a good way to represent what happens in general with the linear transformation. And these cartoons are nice because we can use them to show different cases. For instance, in this particular case, the linear transformation is not 1-to-1. We have 2 different vectors going to 1 vector here. The other thing that this shows is there may be elements in the codomain that are not the result from the linear transformation. So these two, if you remember from discrete math, this is a case where it's not 1-to-1. And again, there may be some linear transformations that are 1-to-1, but this picture shows that this linear transformation is not 1-to-1. This example of a singleton vector here that's not the image of any vector over here, that shows that it's not onto. Let me just say another word for 1-to-1 is injective. And another word for onto is surjective. And if you've been looking at the book, you can recognize those as chapter headings. So we're going to be using this diagram to explain what happens with injective and surjective linear transformations. Okay, so I'll stop there with this video and we'll continue on with the next video.